Welcome to the video on electrophilic aromatic substitution, where we talk about activating and deactivating that benzene ring. So if we think about the reactivity of benzene and electrophilic aromatic substitution, we recall that this acts as a nucleophile. So it is going to reach out and react, form a new bond with some electrophile. If there are already groups on that benzene ring, we could have two primary types of groups. We can have a group that pushes electron density into the ring, and that is called an electron donating group, or we can have groups that pull electron density away from the ring, and that is called electron withdrawing groups. So if our benzene is acting as the nucleophile, think about it. Which is going to be preferred? If our benzene is the nucleophile, is that reaction going to happen faster or slower if we have some group that's pushing electron density into the ring? I hope you see that an electron donating group is going to enhance that reaction. It's going to make this benzene ring even more nucleophilic. Alternatively, if we want the benzene to act as a nucleophile, but we have something pulling electron density out of the ring, that is going to make that benzene less reactive and less likely to act as the nucleophile to reach out to the electrophile. In this video, we are going to discuss electron donating groups, electron withdrawing groups, and we're going to talk about then the reactivity of that benzene ring. Quick little side note, we can have things donating and withdrawing electrons through resonance, and we can have them donating and withdrawing through inductive effect. Remember in class when we drew the resonance structures of those benzene derivatives? When we did phenol, if you remember, we had a negative charge moving around the ring. And this negative charge moving around the ring is going to indicate that phenol is more reactive than benzene because it has a negative charge moving around the ring, meaning that it is activated. Because OH or hydroxyl is an electron donating group through resonance. Ultimately, what happens as well is that this hydroxyl group directs the reaction ortho, para, ortho. We're going to see activation of the ring at the ortho para positions. So this is an electron donating group because of resonance, and it's going to push future electrophilic aromatic substitution reactions into the ortho and para positions. And why is it that phenol is an electron donating group? That is because it has a lone pair on the atom that's on the ring. Because we have these lone pairs that are on the atom, on the ring, they can push into the ring via resonance. Now, if we move down and talk about benzene with a ketone attached, that's going to be something very different. If we look at these electrons, they are not on the atom on the ring. They are one away from the ring. So what that does is that it allows for the electron density to be moved out of the ring. And so in this case, we have an electron withdrawing group. And if we look at that electron withdrawing group, we see that a positive charge is moving around the ring, not a negative charge. This is a positive charge. And what does a positive charge do to a benzene ring that needs to act as a nucleophile? It is going to deactivate the benzene ring. It is going to make that benzene ring less reactive because it has a positive charge moving around the ring, which is going to interfere with it serving as a nucleophile. So electron withdrawing groups slow down the reaction rate considerably to the point where sometimes it deactivates it completely. However, I want you to see if this reaction is just slowed down a little bit and some is still allowed to react. I hope you see the only place on the ring that never has the positive charge is going to be the meta positions. The meta positions never have a positive charge. That positive charge exists at the ortho, para, ortho positions. So we never have positive charge being at the meta positions. So in an electron withdrawing deactivating group on a benzene ring, future reactions, if they're going to happen, will only happen at the meta positions. So if we think about activating groups, one way that we can activate a benzene ring is inductively. So remember, whenever we have a methyl group or an alkyl group of any type, we have a little bit of electron density being donated through the bond. And so that is going to be inductively donating and therefore activating our benzene ring, right? We want the extra electrons to make it a better nucleophile. So we can see right away that the methyl group is going to activate the ring. Toluene reacts much faster than benzene because of that activating group. The second thing that we have to think about is where is it going to push the reaction to happen? So if we think about where the reaction is going to happen when we have an alkyl group, this is called regioselectivity. Where is that nitro group going to go? Is it going to go in the ortho position, the meta position, or the para position? When we go into the lab and do this reaction, it turns out that 63% is in the ortho position. Very little meta is formed. And then we have 34% in the para position. So why is that the case? If we think about the sigma complex and we think about that carbocation intermediates that exist, let's see what happens with that sigma complex if we do ortho attack and then meta attack and then para attack. So in the ortho attack, we end up with 3 resonance structures, 3 carbocations. Here's one, and here's one. This one right here is a tertiary carbocation. This is more stable. In the meta position, however, as we move that carbocation around the ring, it never gets a chance to go to that site. That was tertiary. So this one is going to be much less stable. We come back to the para position. We have that nitro group to the para. Here's the sigma complex. We have a positive charge here, a positive charge here, and a positive charge here. And look, here is the tertiary one again. So when we have the intermediate carbocation at the ortho position and at the para position, we have a more stable intermediate, which is going to make those positions preferred. And so when we have an alkyl group that activates a ring by inductive effect, we end up pushing that reaction ortho-para. Here's energy diagrams to show that that more stable carbocation ultimately has a lower energy barrier, and so we end up having those be the preferred locations of reaction. Why is there more formed at the ortho than at the para? It turns out there's 2 ortho positions. So we get twice as much happening at the ortho compared to the para, but again, no meta. If we want to talk about activating groups that happen through resonance, we can talk about methoxy as well. We have lone pairs on the atom on the ring. Those lone pairs can be delocalized, moving a negative charge around the ring, making it more nucleophilic than benzene itself. And again, because that negative charge exists at the ortho and meta positions, that is where the reaction is going to happen. So if we looked at the reaction where we had excess Br2 and FeBr3 added to anisole, we end up getting only ortho-para products, 100%. So this is called an ortho-para directing activator. If we were adding a nitro group, we don't see any happening at the meta position. We only see ortho and para. So in this case, the para is the preferred product. And I think you can see that's because this group now is bigger and bulkier. And so we're talking about steric hindrance. We can go back and take a look at the sigma complex stability, and this also drives the reaction. There's an additional resonance structure that exists when we have ortho attack and para attack in the sigma complex, which makes that a more stable species as well. And so through resonance, it's not that we have a tertiary carbocation, it's that we have an extra resonance structure for those 2 positions. Here's energy diagrams to show that as well. Because there's additional resonance structures in ortho and para, that is where the reaction will happen. Now, if we talk about deactivating groups, these are groups that are going to take electron density out of the ring. We can have deactivation happen 2 ways. We can have that inductively, and we can also have that through resonance. If we look at the nitro group on a benzene, it turns out that's deactivating in both ways. So it's both inductively electron withdrawing and resonance. The way that it is inductively is that we have a full out positive charge on that nitrogen, which is going to make electron density flow out of the ring to stabilize that positive. In terms of resonance, because we do not have lone pairs on the atom on the ring, we can pull electron density out of the ring to pull up onto our nitro group. So we end up having that positive charge at the ortho and para positions. So the ring is deactivated, so the reaction may not even happen. But if it does happen, it's going to happen at the meta positions shown here. They never have a positive charge. Nitro happens to be one of the strongest deactivating groups, by the way. So if we have a nitro already on our benzene ring, we're going to see that when we add a second nitro, 93% goes in the meta position. Here's what I was just talking about. Nitrobenzene undergoes nitration 100 times slower than benzene. So that is pretty substantially deactivated. If we take a look at our sigma complexes and see if this supports the meta attack, it certainly does. So when we look at the meta attack here, we see that we have 3 stable carbocation structures. Once we look at the ortho attack and the para attack, we see that we have a structure where we have a positive charge on a carbon right next to the positive charge on the nitrogen. And so that is a highly destabilized species, which makes this sigma complex less stable than the meta. And then we see the same species existing in the para attack, where we have a positive charge on the carbon that's right next to a positive charge on the nitrogen. And so that's a destabilizing effect. Again, this reaction is going to happen at the meta position. Sigma complex analysis of this reaction supports the meta attack. And here's the energy diagram for those reactions. We see that at the ortho and the para positions, that's going to be much higher in energy, harder to get to. Up until now, we said that all electron donating groups are ortho-para directing. And up till now, all electron withdrawing groups are meta-directors, except the halogens. So think about a halogen. Let's say bromine is on the benzene ring, and it has lone pairs. It has lone pairs on the atom on the ring. It is going to donate electron density through resonance into the ring and push it orthopara. At the same time, however, because bromine is highly electronegative, we are going to have some electron withdrawing capabilities of the bromine as it's holding very tightly onto those electrons. So we are going to have inductively withdrawing, and we're going to have donating through resonance. So they fight it out, and it turns out chlorine and bromine are going to be inductively withdrawing electron density, making that less reactive. But at the same time, they are going to be pushing electron density into the ring because they have these lone pairs on the atom on the ring. So we ask ourselves, what wins? Is this going to be a deactivating group or an activating group? And where does the reaction happen? This is overall a deactivating group. So the halogens deactivate the ring, but only slightly. So there's just a little bit of deactivation. But because of that negative charge in the resonance structure that moves around to orthopara, that is where the reaction happens. So halogens are orthopara directing deactivators. They're the exception. And if we look at the sigma complex, we can see if we have ortho attack and para attack, we end up having that additional resonance structure. I know it looks crazy, right? That positive charge is up on the chlorine, but that's okay because that charge can be delocalized to the chlorine in addition to the 3 carbons within the ring, then that makes that preferred. And so we do not get meta attack. We get orthopara attack if we have a halogen on the ring already. So it's deactivating only slightly, and it's orthopara directing. So here's a table that kind of summarizes everything. Right here is benzene. Anything above it is more reactive than benzene. Anything below it is less. So that means anything above it is going to be activating, and anything below it is going to be deactivating. We have inductive effect here. They're going to have a little bit less of an activation because they're just inductive. We have all of our resonance activating groups up here. And notice they all have lone pairs on the atom that's on the ring. And these all are going to push orthopara. Now, if we look at our deactivating groups, here are the halogens that we talked about. Halogens are going to be deactivating only slightly because of that whole conflict of the inductive and resonance, the fight that goes on. They're going to be slightly deactivating. They're going to push the reaction to happen at orthopara. And all the way to the left, when we talk about the deactivators that are substantial, these are going to be primarily through resonance, and they're going to be meta-directing. And notice we have lone pairs on the atom, one away from the ring in many of the cases. Now, if we take a look at the 2 very strongly deactivating, that's going to be nitro because that's inductive and resonance fighting the same fight. So they collectively make the ring very deactivated. And then this last one right here is going to be inductively, and that's because we have a full out positive charge on that nitrogen right next to the ring. So here are the strong activators, orthopara directing. And here are the moderate activators, ortho-pair directing. Here are the weak activating, and that's going to be through inductive effect. Here are our very strong deactivators, and here are our moderate deactivators. And so then the very, very weakly deactivating are going to be the halogens. And remember, those are weird, right? Those are ortho-pair directing. At this point, we are going to have to memorize these, except I hope I've taught you how to think about it so that you don't have to actually memorize everything. You kind of already understand it. Okay, there you have it. Activating and deactivating benzene rings.